Hello, my name is Jianning and I'm from Glasgow University of Technology. Today, I'm going to present our work on automatic cranial implant design, which can serve as a baseline for the MICCAI 2020 AutoImplant Challenge. Cranial implant is used to repair the skull defect caused either by a brain tumor surgery or by trauma. Currently, clinically usable cranial implant is usually designed interactively and involves several steps: acquisition of the 3D skull model, mirroring the undamaged side of the skull to the defective side, and post-processing. It can be an expensive and time-consuming process as the implant needs to be designed by professional designers using commercial software and manufactured externally or hospital. A fast and automated cranial implant design pipeline is therefore highly desired in clinic, as it can enable manufacturing of the implant directly in the operation room via a 3D printer. So, how the medical problem, cranial implant design, can be technically formulated? On the one hand, designing a cranial implant is equivalent to restoring the missing portion of a defective skull. The implant can then be obtained by taking the difference between the two skulls. In this sense, cranial implant design can be formulated as a shape completion problem. On the other hand, the missing portion can also be predicted directly without the intermediate step of completing the defective skull. Previous work regarding skull reconstruction mainly falls in two categories: statistic shape model, SSM, and deep learning. Both approaches are fully data-driven, and the defects are created artificially from healthy skulls. This is because real skull defects from craniotomy or from trauma are rare, and they are often lack the ground truth. In contrast, complete skulls are much easier to acquire in large quantity, and there exist public skull dataset, such as CQ500. The difference is that SSM usually processes skull mesh, while deep learning-based methods process the skull volume. The challenges of using deep learning-based methods for skull reconstruction lie primarily in two aspects. First, the skulls segmented from head CT are of high dimension, usually 512 times 512 times the number of slices. Second, cranial implant has to be consistent with the defective skulls in terms of the defect boundary, bone thickness, and shape. The shape of the implant should be consistent with the remaining portion of the skull so that the implanted skull can look like a normal one. It is difficult to learn high-dimensional shape in a fully data-driven manner, and the previous publications regarding shape reconstruction usually rely on the geometric priors of the shape. The dataset we are using is adapted from a public head CT collection, CQ500. Altogether, 200 undamaged skulls are selected. Then, the skulls are segmented from head CT using thresholding. On each skull, a portion of the skull bone was removed automatically to simulate the brain tumor removal surgery. This process results in a defective skull as well as the corresponding implants. We are trying to make the virtual defects realistic and include the cranial drill used in craniotomy. Considering that in real surgery, the defects are varied in terms of shape, size, and position, depending on the intracranial pathology to be operated on for each particular patient. We include also some variations in the creation of the skull defects. The shape variation of the defects mainly comes from the skull, as each individual skull has unique shapes. The position variation is defined as the starting point coordinates of the bounding balls of the defected region. We can see from the box plots that the position variation mainly comes from the Y and Z direction for both the training and test set. The size variation is defined as the size of the bounding box of the defective region. We can see that the size variation also comes mainly from the y and z direction. As introduced just now, one of the challenges of skull processing is the high dimensionality, especially when the available GPU memory is limited. We therefore propose a coarse-to-fine framework for high-resolution implant generation using a GPU with only 8 GB storage. First, a network N1 is trained to predict coarse implants from downsampled skulls. Even if the coarse implant is low resolution and lacks geometric details, it carries the spatial information of the defected region. Second, based on the spatial information, we extract the defected region from high-resolution skull with some surrounding information. Third, another network N2 is trained to learn high-resolution implant directly from the defected region. We can say that the whole process avoids dealing with the original high-dimensional skull directly. Instead, it deals with the downsampled skull and then process only a portion of the original skull, which contains the defected region. By doing so, the two networks, N1 and N2, can be trained on a GPU with limited memory. Next, we talk about how the framework can be implemented in detail. There are 3 questions. First, how to extract the defected region. Second, how the two networks N1 and N2 should be chosen to suit the purpose of implant generation, while at the same time contains the GPU memory. And third, how to transform the implant back to the original dimension. Let's look at the first question, how to extract the defected region. It involves 5 steps: coarse implant prediction, upsampling, bounding box calculation, applying margin, and applying zero padding. First, the original high-resolution skulls are downsampled to 128 times 128 times 64 dimension. On the downsampled skulls, a network N1 is trained to predict coarse implant of the same dimension. Then, the coarse implant is upsampled to the original dimension, 512 times 512 times number of slices. We calculate a bounding box on the upsampled implants, and the bounding box tightly encloses the defected region on the original high-dimension skull. A margin of 20 voxels is applied to the x and y axis of the bounding box to include some surrounding skull bones. Considering that the size of the bounding box are different, we apply zero padding to each bounding box so that they can have a uniform dimension. Finally, we train another network N2 on the extracted region to learn fine implant directly. The second question is how to choose the two shape learning networks N1 and N2. In our work, we use 2 standard autoencoder style networks for both N1 and N2. As the input size of N2 is much larger than that of N1, we have to restrict the complexity of N2 given the limited GPU memory. Specifically, N1 has about 82 million parameters, while N2 has only about 0.6 million parameters. Regarding the third question, the implant produced by N2 has a dimension of 256 times 256 times 128. However, the dimension of each implant has to be consistent with that of each corresponding skull, which has a dimension of 512 times 512 times number of slices. This can be done by using an inverse process of zero padding and margin applying. Our proposed framework achieved an average of 0.85, 5.18, and 0.15% for dice score, host of distance, and reconstruction error, respectively on the 100 test data. For qualitative evaluation, the proposed implant can match with the defect scores in terms of defect boundary, bone thickness, and shape. We compare the two implants produced by N1 and N2. We can see that even if the coarse implant from N1 can be upsampled to the original 512 dimension using interpolation, the surface lacks geometric details. In contrast, N2 can not only reconstruct the shape of the implant precisely, but also restore the geometrical details of the surface. The red, green, blue color map shows the host of distance between the predicted and the ground truth implants. We can see that they match very well, especially on the border of the implant. There are two main limitations of the study. First, the models are trained and evaluated only on synthetic defects. Second, N2 tends to fail on highly varied defects. We create 10 additional data for testing with much greater variations regarding the position, size, and shape of the defects. However, we found that N2 cannot make correct predictions on those cases. To conclude, our study has 4 contributions. First, we demonstrated that high-resolution shape learning can be fully data-driven without relying on geometric priors. Second, to save computation, shape learning can be carried out only on the defected region with limited surrounding information, instead of on the entire skull. Third, most importantly, we propose a coarse-to-fine framework that facilitates the processing of high-dimensional data with limited GPU memory. Last, the approach can serve as the baseline for the MICCAI 2020 AutoImplant Challenge. N1 and N2 can be better designed to improve their respective performance. Our future work will focus on creating more realistic defects and providing real cranial anatomy data for evaluation for the challenge. Okay, thank you for your attention.